In a previous video, I said that the inverse Laplace transform of some function, that this is a linear operator, so it exhibits linearity. This is true. I also said in that video that I didn't quite know why it was linear or how to prove it, but actually I do know now because I just read my textbook, and it's fairly simple to prove. So if we say that some operator has linearity, what we are saying is two things. Let's assume that we have two functions, well, three, f1, f2, and f3, where these are just all arbitrary functions. Don't worry about what they are. They're just there for the sake of being there. And these are all solutions to some Laplace transform, which is why they're capital Fs. Then if the inverse Laplace transform is to be linear, it must exhibit that the inverse Laplace transform of the sum of two functions, f1 plus f2, is the inverse Laplace transform of f1 plus the inverse Laplace transform of f2, and also that the inverse Laplace transform of some constant, so let's also just define some constant, which is a real number, just some real, and also that the inverse Laplace transform of a constant times another arbitrary function, that this must always be that constant times the inverse Laplace transform of that arbitrary function. So you're probably going to see a lot of melted curly braces in this video. Now, if the inverse Laplace transform is true, these things are going to be true. So we'll put question marks next to them. We don't know if they're true. We kind of hope they're true because we know it's linear. So in hindsight, this definitely should be true. But let's say it's first time venture. We're trying to prove it's true. Well, because the inverse Laplace transform is a well-defined inverse, which is to say, for every Laplace transform, there is one inverse Laplace transform, and for every inverse Laplace transform, there's one Laplace transform, we can use the Laplace transform to prove some of these properties. So let's take the Laplace transform of both sides of the first here. What we're left with is that we have, I can probably even just copy and paste this to make things even simpler. We have let me erase some of this junk from the bottom. What we have is this. And now if we take the Laplace transform of both sides of it, we get the Laplace transform of all of this equals the Laplace transform of all of this. Now we know for a fact that the Laplace transform, based on its integral definition, is itself linear. So we can say that this right-hand side, again we still don't know if it's equal, this right-hand side is, breaking apart by addition, is going to be the Laplace transform of the inverse Laplace transform of big F1 plus the Laplace transform of the inverse Laplace transform of big F2. And then the right-hand side, by the definition of any inverse function, if you take the function of the inverse of something, it's just that something, f1 plus f2. And now we have the exact same thing on the right-hand side, where we're seeing that we have a function and then its inverse. So we take it out, okay, we say, all right, well then f1 plus f2, if this is to be true, must equal, well, f1 plus f2. And this for sure is true. So great, we just proved our first property. You put a check mark next to it. The second property falls similarly. If we were to take it and say, all right, so we need the inverse Laplace transform of some scalar times some function to equal that scalar times the inverse Laplace transform of the function, then let's just try taking the Laplace transform of both sides. The Laplace transform of this side times the Laplace transform of this side. So what we're going to be left with is the, again, Laplace transform of an inverse Laplace transform of something. It's just that something. So CF3 on the left-hand side equals, and by our property of linearity of the Laplace transform itself, we can take this C out. So we say C times, and then the Laplace transform of the inverse Laplace transform of f3. And we don't know if this is true, so we'll keep our question marks. But now what we say is CF3, therefore, must equal, if this is true, C times, again, same deal, Laplace of, inverse Laplace of f3, That's just F3. F3, and this is clearly true, so we give it the big check mark. Big check mark. So it is actually fairly straightforward to prove that the inverse Laplace transform is linear because its inverse, the Laplace transform itself, is also linear. So linearity, give it a check mark. See you in the next video.